Recall that in the previous field theory video, we proved that the irrational number E is transcendental. Now in that proof, we came across quantities like this. Epsilon I two minus I theta I whole to the power p, etc. n minus I theta I whole to the power p times I theta I to the power p minus 1 times I divided by p minus 1 factorial. In the previous video, I actually made a mistake in writing these expressions because I forgot to write I. But that's not why I'm making this video. The thing is that I think there is a legitimate error here in the proof, and where the theta i's are real numbers lying between 0 and 1 for I varying from 1 to n. After this, what the author says is this. He then estimates the sizes of these theta i's and writes an upper bound like this. N factorial to the power p divided by p minus 1 factorial. Now parts of this upper bound are easy to understand and they are true also. For example, when you take the absolute value of epsilon, minus sign of course vanishes and you are left with p minus 1 factorial in the denominator. In the numerator you have these things. Two minus I theta I to the power p, etc. N minus I theta I to the power p times I theta I to the power p minus 1 times I. Okay, now let us do some small calculations here. Let's first show that this is less than or equal to e to the power n. And all of these things are after fixing some I. That is understood. Okay, we have considered some integer I in this range, and after that we are doing this calculation. Now in this part, theta I lies between 0 and 1. This implies 1 minus theta I also lies between 0 and 1. 1 minus theta I is positive because theta I is less than 1, and 1 minus theta I is less than 1 because theta I is positive. I think I said something like this in the previous video also. Now this implies if we multiply throughout by I, the inequalities will remain intact. Intact in the sense that they will not get reversed, and that is because I is a positive integer. Okay, so we get this is less than I. Just give me one moment. Okay. Is less than I, and I itself is less than or equal to n. So from these inequalities we directly get this. less than or equal to e to the power n. And because the exponential function, real exponential function, is always positive, it is never 0 and it is never negative, so this is equal to its own absolute value, less than or equal to e to the power n. So we can write e to the power n here. So that's what we have here. So this part we have got. What else can we say? What about this part? This is in fact easier. It comes directly from these inequalities. Now instead of going to 1 minus theta I, you just multiply here itself throughout by I. That gives you I theta I less than I. Okay. So if you replace I theta I with I, then that means you are writing more. So it's okay with this inequality. Or in fact, let us just do the calculation here itself and then we will write the final thing. I theta I to the power p minus 1 times I is less than or equal to I to the power p minus 1 times I, which is equal to I to the power p, and because I is a positive integer, so there is no need to write absolute value, and because I is less than or equal to n, so we get this. So in place of this we can write n to the power p. Then looking at this, it is clear what the author has done. He has replaced this with 1, this with 2, etc., this with n, and obtained n factorial to the power p. But here there is a problem. You see, if one just simply looks at it in a haste, okay, not thinking very minutely about the situation, it seems that it's okay, because here we are subtracting I theta I from 1 and I theta I is positive. Theta I is a positive real number, I is a positive integer, so I theta I is positive. So if we don't do that subtraction, that means we are writing more. So actually this should be strictly less than 1, like that. This should be strictly less than 2, etc. That would be fine unless you have a situation like this. Say we consider the first one itself. The first one says that this is less than 1, or for the sake of being somewhat relaxed, let us consider it to be less than or equal to 1. Actually it will be less than 1 if it is actually less than 1, because this is positive, this is not even 0. But if we have a situation like this, is this true? Definitely this is not true. This would be true if I theta I is not just positive but itself is less than 1. Then it is true. In that case, you can simply write 1 minus I theta I, because that is positive and that becomes the absolute value itself. Now this is less than 1 simply because I theta I is what? I theta I is positive. Note that for this inequality to be true, it's enough that I theta I be positive. That is true. I theta I is positive for us. However, this does not imply this. Unless you know that I theta I, besides being positive, is also less than or equal to 1. If that is not the case, then you get a situation like this. I theta I here is positive, it is 3, but still 1, it's greater than 1. So although 1 minus 3, which is minus 2, is less than 1, the absolute value of 1 minus 3 is not less than 1. Okay, now comes the point. You may think that no, maybe the author has not actually replaced this with 1, this with 2. Maybe he has done something else, so that the end result of this is that this product is less than or equal to n factorial to the power p. But I don't see any such hidden calculation or any room for such calculation. In a pretty straightforward manner, it has been written that this thing is less than or equal to n factorial, and that too, that is clearly obtained by such a replacement. And this is definitely a mistake. Okay. But there is one more thing, that there is one place where you can question me. This 3 is only an example, only a situation that may arise. No one is saying that this will arise here. You may try to argue like this. Maybe the theta i's are so small, because they are less than 1, that the I theta I will be less than 1. However, I don't see that necessarily happening. Recall where these theta i's are coming from. Let us go back to the proof a little bit. In the proof, what we did, we first considered a polynomial of degree r with real coefficients. This has degree r. And then what we did, we considered this function plus the first derivative of f plus the second derivative of f, like this, plus the nth derivative of x. These derivatives exist because f is a polynomial function, and polynomial functions are infinitely differentiable. We know these things from calculus, and the derivatives themselves are polynomials. So this capital F of x itself is a polynomial function, so it is also differentiable. Then what we did, because this is differentiable, the product of capital F with the exponential function, which is known to be differentiable, is itself differentiable, this product. And one can consider this product function on the closed interval 0, k, where k is any positive integer. Then what we did, utilizing the differentiability of this function on this closed interval, we were able to apply the mean value theorem from calculus. In that mean value theorem, we obtained these theta i's. So the theta i's for this general polynomial f, the theta i's will depend on everything, not only on small f but also on the, because capital F ultimately depends on small f, but at the same time also on this interval. Okay, so as k changes, as k increases from 1, 2, 3, etc., we in fact considered n values for k, the first n positive integers. So on k and f, this theta i's will depend. But this is only the beginning of the proof. What we then did, we considered a specific polynomial which looked something like this: 1 divided by p minus 1. I don't remember whether we had factorial here itself or not, but we had something like this: 1 minus x to the power p, 2 minus x to the power p, etc. Maybe n minus x to the power. This was the general structure of the polynomial that we took, and then for that polynomial we then wrote all these things. And so this is a very general situation. Note that this polynomial, which we call a Hermite polynomial, is not a fixed polynomial. It depends on this prime, and this prime itself was chosen based on some two numbers. One is n and the other is c naught. You go back to the proof, you will see that the prime p was chosen to be greater than n and greater than c naught. Now one may argue that all these things ultimately lead to the situation that these are all without the modulus. These expressions are actually positive real numbers. But nothing has been said about the positivity of these things or the lack of positivity of these things in the proof. And in such a complicated situation, I don't see that these expressions are always going to be positive. Specifically, it's very difficult, even without going into all the complexities. If you just simply look at this itself, this inequality, note that I can take any value from 1 to n. So if you take n itself, for that also this inequality should be true. That is, we should have this. If what the author has done is correct, then we should have this. Now, do you think that our n, which we are choosing freely, we chose n somewhere in the beginning itself, n can be chosen very large. Now, from the mean value theorem, the theta n that you are getting, which really is, it represents a point in the middle of the interval 0, n. That theta n is so small that n times theta n is always less than 1. It is hard to believe that that is going to happen. But the main point here is that, do you really think that the author has suppressed so much detail and has not even mentioned that these quantities are positive so that this bound is true? I don't think so. If there was that much subtlety in the proof, it would have been made a part of the proof itself, because this is not something that one can easily see. No, we don't know from the situation that this is always going to be the case. It's very likely that this is not the case, and that's why I think with I'm almost sure that this is a mistake. In place of this part, you cannot actually write n factorial to the power p. Okay, that's a mistake according to me. If you can convince me otherwise, please go forward. But I think this is an error in the proof. Okay, now if this is really an error in the proof, how can we rectify? Can we rectify this? Because otherwise this proof is gone. Let's see what we can do. I have written so many things here. Let me just wrap up the inessential parts. Okay, I have to write this part now. 1 minus I theta I to the power p, 2 minus I theta I to the power p, etc. n minus I theta I to the power p. Okay, fine. So it seems we cannot replace this by 1, this by 2 to the power p, etc. But can we replace each one of them by n to the power p? Let us see if that is true. Is this true? Is this true? Suppose this is true, then it is equivalent to these inequalities I theta I less than or equal to n, which in turn are equivalent to these inequalities minus n minus 1 less than or equal to minus I theta I less than or equal to n minus 1. And continuing here, these inequalities are equivalent to, now if we multiply throughout by minus 1, the inequalities they change direction, greater than or equal to I theta I, this is greater than or equal to 1 minus n. Okay, let us now think of this situation, whether these inequalities are true, because if these are true, then this is true. What about the first one? Note that I theta I is less than I, because we can multiply on both sides here this part of the inequalities by I, and we get this. Now I is less than or equal to n, so I is strictly less than n plus 1. So that means this is indeed less than n plus 1. This is true. Okay. Now no matter what n is a positive integer. So in the worst case scenario where n is as small as it can be, when n is 1, this is 0, and clearly I theta I is greater than or equal to 0. In fact, it is greater than 0. Theta I is positive and I is a positive integer. And if n is greater than 1, then this becomes negative. So we have, in fact, we are more convenient, in a more convenient position. So this inequality is also true. So that means this is true. Now if you have any other positive integer k in its place, will things change significantly, where k itself is in between 1 and n. Let's see. So we then have this, and here we have n minus k. So that means n plus k, here we have k minus n. Okay. we are in fact in a much better position in this with this first inequality. We have already shown that I theta I is less than n plus 1 and n plus 1 is less than or equal to n plus k. So this is all the more true. What about this second one? K is less than or equal to n. So that means k minus n is non-positive. K minus n is less than or equal to 0 because of this inequality, and I theta I is positive. So yes, it does not matter what we have here, we can write in place of all of these absolute values n. Okay, in each one of them we can write n. So that means the bound we have here will now change. But will that bound be useful? That is another question. Let's just take one step at a time and see how far we can go. So now, instead of having n factorial, we will have n to the power p, n to the power p, n to the power p, etc. like this. N to the power p, how many? N number of n to the power p's. Counting this 1, 2, 3, etc. up to n, combined with this extra 1, this bound now becomes okay, so this will become n to the power n number of p's and one extra p, so n plus 1 times p. Okay, this is large. Now after this, what originally the author says is this: as p increases, this is equal to, this limit exists and it is 0. These quantities approach 0. Can we say something similar here? And I originally planned to prove this by showing that this series is convergent. E to the power n, n to the power m times n factorial to the power m Now if I proceed similarly here, is this series convergent? E to the power n, n to the power n plus 1 times m divided by m minus 1 factorial, where m varies from 1 to infinity. Is this series convergent? Let's apply the ratio test. The m plus 1, note one thing, that in this series, although n is some positive integer, but in this series n remains fixed. N does not change, only m is changing, that is the index. So the m plus 1th term is this divided by the mth term. Now what happens to this expression? this expression becomes, there are some cancellations, and what do we have here? N to the power n plus 1 times m plus 1 minus n plus 1 times m. That means n to the power n plus 1. N to the power n plus 1. And if we cancel m minus 1 factorial with m factorial here, I mean if we do the cancellation, then we get m. So as m approaches infinity, this approaches 0. So by the ratio test, this series is convergent. And from that convergence and from elementary properties of series of real numbers, we know that this limit is equal to 0. Of course, if one uses properties of limits or some known limits, one may not need to go to series and do something like this. But I think this, I feel this is better for me. You may prove that this limit is equal to 0 in some other more direct way. Anyway, so this means that this sequence is convergent and has 0 limit. So its subsequence, where in place of any positive integer m, you have the primes, whose general term looks like this. This subsequence, where p is a prime, that means the index p now varies over the set of primes. This subsequence is also convergent and it converges to 0. So that means our new bound also approaches 0 as the prime approaches infinity. So that also serves our purpose. So although there is an apparent mistake, I say an apparent mistake because I don't know if some very intricate and complicated inner working of this part actually leads to this bound. But we don't have to bother about that now, because there is a much easier way of also getting the job done. So that means the proof survives. Of course the proof survives, it's an old proof. Maybe this is a very small mistake no one has noticed yet, but we can salvage things in this way. Okay, so yeah, so I thought that we will encounter some pretty strange difficulty in overcoming this situation, but things fell into place quite nicely with this new bound. So in the next field theory video, we will continue with these things. Okay, and according to our schedule, tomorrow we have that vector space and modules upload. So with this rather small video, but it's an important one because our confusion has now been cleared. Now there is no confusion. So with this I end this video. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.